let's resume this class. We ended the class just as the cusp of Nernst equation, and today we will talk about exactly how you apply the Nernst equation, why the membrane potential of a cell is at -90, because if you understand that, life will become a whole lot easier. You will understand what is action potential and how it works and what are the basic prerequisites. Now, we ended the class telling you the cells are sitting at -80, -70 and sometimes at -40. I am purposefully not talking much about it at this stage, but I will eventually talk. There is a reason for it. So, now I told you that outside life has evolved from C, there is a lot more sodium. To the point, if you want to remember it, it is almost 12 times outside. So, if it is almost 144 liters, something like this, of sodium and chloride outside, you will have only approximately inside, it will be around 12, something like this. You can cross check how much sodium is in extracellular fluid versus sodium in intracellular, which is inside the cell, right. So, outside sodium and chloride are very high. I have already discussed this with you. It's basically sodium chloride. I am drawing it in the ionic dissociated state, whereas inside there is a lot more potassium. Now, think of the situation exactly in the last class what I was trying to tell you, and outside potassium is pretty less. Now, here is exactly the situation of this. Apart from it, there is something more. All these structures have lot of proteins inside, P's, okay, in the mitochondria, and this. Most of these proteins are negatively charged, okay. Most of these proteins are negatively charged. So, now think of the left hand side of the drawing what I drew for you. I showed you like P, these are those proteins. Imagine this side, your left hand side, LHS is inside the cell and this RHS is say outside the cell, and this membrane is the semi-permeable cellular membrane, which is particular to allow certain things to flow, certain things not allowing them to flow. So, these are those different kind of proteins which are present there, which cannot, mind it, which cannot travel from left hand side to right hand side, or means from inside to outside. It means they are all anchored inside. So, that means inside the cell there is lot more negative charge, and that is why you get a -90 millivolt. But how you can mathematically deduce it? That is Nernst equation, because this is, you know, these values, but they cannot be determined so easily, because you need micro ionophoresis and all other techniques, micro syringe, micro needle to pull out the fluid from inside the cell and measure how much sodium is there, how much chloride is there versus outside, and so it's a pretty complex process. How do you know? How do you plug in? Now, what you do is the equation. Now, if here in C inside, say for example, instead of, so this C stands for concentration, this is the log and this is the in millivolt, right. Now, if you plug in the values, say inside it is say 12 of sodium and I say 144 outside, then it becomes 12 ones are 12, 12, 1 by 12. Now, if you resolve the value, you will find what is the potential difference of sodium ion only, fine. Now, you similarly do it for potassium ions, inside versus outside. Similarly, you do it for the chloride ion, outside, inside, and you will get three different kind of values. Say you will get ENA, EK, ECl. Now, and any other atoms which are present there, ion which are present there. If you add all of them, you try this exercise, you will land up with this value or this value, depending on what values you are picking up. And this is the beauty of Nernst equation. And as a matter of fact, the extension of Nernst equation is called GHK equation. Goldman, Hodgkin, and Kurtz. Goldman, Hodgkin, and Kurtz equation, which is nothing but exactly, I can write here plus and plus what I was telling you to add, ENA plus EK plus ECl. You sum this up, you get the total membrane protein. So what you get here is you add all of them, you will get, so you add all of them using GHK equation, which is nothing but extension algebraic addition of the Nernst equation, and that will give you the value of minus 80 millivolt. So look at it, how these fundamental studies have changed our understanding about why we get these values. Let's say, for example, this particular value, why they are sitting there. So this is how you have to do the calculation. Why this calculation is important. Now you might ask a question, is how this thing happens, how action potential is being shoot. Now this brings us to a non-linear phenomena which happens in the cell, and this non-linear phenomena defines the fate of a cell, whether we call it an excitable cell or a non-excitable cell. And that is what we are going to now discuss. How this could happen based on Nernst equation, they are all balanced. There is minus 80 millivolt, minus 90 millivolt. Then why they are shooting up like that to make the membrane potential 0 and overshoot further than 0, say plus 10, plus 20 millivolt, and it comes back. Though this event is for a very brief period of time, but it does happen. And understanding this phenomena was done by two British scientists who completely explained the whole process. Prior to that, there was a gentleman called Bernstein who saw this phenomena, say this is as if a cell is having a load shedding. It completely goes off and then it comes back into life. It was done by Hodgkin and Huxley. And this is one of the landmark discovery which was again happening when the whole world was busy figuring out the structure of DNA, while Watson and Crick and all these people were very, very busy. It was in that backdrop. Little prior to that though, the world was much more busy on the genetics, because by the time the Mendel has rediscovered and the whole world was moving towards genetics, that time Hodgkin and Huxley came with what they called Hodgkin-Huxley formalism, which for the first time, without any knowledge of structural biology or knowledge of crystallography, there was nothing, no such a structure was known, of no idea of membrane protein. Not only that, people were not even aware of the structure of the membrane. It is a lipid bilayer. There was nobody knew how the membrane looked. It was after that the theories of Dixon, Joly, and eventually multiple theories which came. The lipid bilayer model was made, but that was back in 1960s. But what I am talking about is 1930s and 1940s. Is the time of some of the biggest celebrations in the field of bioelectronics, and which eventually today we know the whole electrophysiology and biosensors, they all have their basis to some of these very, very fundamental discoveries which were done. It was called Hodgkin-Huxley formalism. And again, remember, there was no knowledge of membrane protein, membrane channels, membrane pumps, pores, nothing was known. It is purely a formalism based on the movement of what was being observed in sea slug. They observed by inserting electrode inside the cell. So, something what I drew for you guys. Yeah, inserting electrode inside the cell, E inside versus E outside, and changing the fluid, extracellular fluid, and using Nernst equation for their rescue. They could deduce, using a whole range of mathematical tools, they could deduce the whole concept of action potential. Now, what really is action potential? We talked about the Nernst equation. So, now we will talk about what is an action potential. Okay. So, life was easy, that cells are sitting at minus 90 millivolt. This is their voltage across the cell. Yet few cells have this bizarre habit of shooting something like this. Y axis is voltage in millivolt, x axis is time in milliseconds. Now, this can only be explained without any knowledge of anything if we again go back to our diagram. This can only happen provided all these C's or proteins which are there, we showed the previous diagram will be easier for you to understand. If these P's and C's which are permanent negative charges, they cannot move to the other side, moves out, and they leave the whole cell with lot of positive charges. But these are huge molecules. By assumption, it is very tough to believe that they are going to travel to this side because they will take time. So, bulky people, they are with lot of luggage, they cannot move most likely. Then what could happen? Only other way you can explain it, lot of this positive charge transiently moves inside. Then only it is possible that define how all of a sudden you see a positive inside and negative outside. So, what is happening here if you look at this diagram? So, if we keep this configuration as intact, so initially you are reading this and then suddenly you start to read this. So, it means with initially it was something like this. These are negative charges versus positive. It's like a battery. Suddenly, you observe a different kind of situation where and this is where you are measuring is this point, right? And of course, the same configuration of measurement. Here is an electrode, you are measuring the voltage outside and inside, right? Again, soon after that, the third configuration, if this is the stage 1, this is stage 2, now comes the stage 3, where back to here, even more negative here. Then a stage 4, if this is the third stage, this is the fourth stage, where again the same positive, positive, positive. What do you see? Baseline again with the baseline. What really happened? As I have already mentioned, those big proteins and organelles cannot come out, which are harboring lot of negative charges. Then something is moving. Without this movement, nothing can happen. What is the most putative molecule which could move? Outside, potassium is low. Few potassium moving inside the cell won't make any hell heaven difference in the cell's life, right. Only molecule or only ion which can flushes inside and bring a lot of positive charge could be none other than our this guy. They are abundant outside, lot of them. As I mentioned, like if you really put a value to them, then something like this. Where was that? I'm just trying to search where I was mentioning you that if you put, they are abundant outside. Only logical reasoning could be lot of sodium moves inside. Now, if lot of sodiums are moving inside momentarily, then when it is coming back, is it lot of this potassiums which are going out or sodium which entered goes back? And this is 1930. Today you are almost inching towards 2030. Technology was somewhere else. Now you understand, and this is in the backdrop of 1930s and 1940s, or maybe say 45. Okay, the world was reeling under two World War I and World War II. And people who were trying to answer this question, one of them was Royal Air Force pilot among Hodgkin and Huxley. Now, how do you justify what is coming out? Because as I have already mentioned that inside there are a lot more potassium. So, potassium can go out, it is potassium going out. If potassium is going out, then inside it becomes all sodium, then this cell will no more become active or no more live, because it will desiccate through. You remember when I mentioned, if you go back to this part of the game in the last class, when I talked about somewhere it made a shelter so as to ensure that it is no more living in that high sodium concentration. If sodium remains inside the cell and potassium goes out in order to maintain its balance, then there is no way we will be able to see the second action potential, because this cell is going to desiccate out, maybe a couple of them, and then it is slowly going to die out. The cell does not die off, it keeps on shooting these kind of action potentials for prolonged period of time. How that's feasible? That is where comes the most celebrated thing. What I was trying to explain to you is Hodgkin and Huxley formalism, and what they figured out from this. There are three things they figured out from this whole process. Step 1, diagrammatically I will show you. Lot of sodium enters in a flush, and I will talk later why they are entering, what made them to enter. Step 2, this is not enough, there is efflux of potassium. Third point, what they figure out by some unknown means, what they have mentioned, because they are not aware of pumps. Sodium are being thrown out and potassium is being brought back. There are three critical events which are happening. So, in the next class, we will talk about these three events and wind up this part of action potential generation, because that is the key for excitable cell, excitable whole cell biosensing. Okay, thank you, and in the next class we'll talk more about it.